Okay, so we are going to discuss shear modulus or modulus of rigidity. So as we know, stress is directly proportional to strain. Here, shear stress is directly proportional to shear strain. And if we want to know what is the constant of proportionality here, we refer this constant of proportionality as shear modulus or modulus of rigidity. Now, if we want to know further, this is force per unit area. This force is tangential. We have already discussed about this thing. Let me check it. Okay, here tangential or shearing stress, and then there is shearing strain. And look here, shearing strain is this length, and this is change in its dimension here. Means how much it has been slided this side. So ultimately, it is change in this length or this displacement per unit this original height here, and ultimately it will come nearly theta, the angle by which it has been shifted here. So let's get back to the discussion. So this is tangential force per unit area where it was being applied, and then this is g, and this is delta x, what was displacement there, and per unit this length. So in other words, we can write it as, let's say this is only sigma s here, shear stress equals to g, and this was the angle at which the surface was displaced. Now we know this modulus of rigidity or this shear modulus can be related to this Young's modulus. We have discussed it by this term. So this thing we can arrive experimentally also by observing the values for different materials. Okay, now let's take a table where we are going to see the modulus of rigidity for various substances or materials. Okay, so here we have for aluminium, brass, this is in gigapascal here, means 10 to the power 9. So we know 10 to the power 9, the prefix used is giga. 10 to the power 6 we use mega, and 10 to the power 3 times we use kilo, and so on. Start our discussion about example this 8.4 square lid slab side 50 centimeter. Okay, it is given here, this length is 50 centimeter here. Let's say this is L equals to 15 centimeter, and thickness is 10 centimeter. So this thickness is 10 centimeter here, and this is from here to here it is 50 centimeter, and from here to here it is 50 centimeter also. Okay, so these two sides are 50 centimeter, and this is its thickness, which is 10 centimeter. Now a shearing force on narrow face means on this face, a tangential force is being applied, and the force is 9.0 into 10 to the power 4 Newton. This is force. Now the lower edge is riveted to the floor. This edge has been kept fixed, and now this face is allowed to be sliding here. Now how much will the upper wedge will be displaced? Means we have to find out this displacement to here, what we are referring as delta x in our discussion. So force is given, area we can find out. This is from here to here is 50 centimeter, and this is 10 centimeter. So the area on which this force is being applied is 0.5 meter times 0.1 meter, and you can write 0.05 meter square. Now you can get what is the shearing stress here. So let's say this is delta S, and we have to write F by A, and if you calculate, it will be nearly 1.80 into 10 to the power 6 Newton per square meter. Okay, now what about G? So we can take it from table as we have discussed. This is lead slab. So for lead, so it is 5.6 into 10 to the power 9. Okay, now what about this length? This is 50 centimeter. So here we have L equals to 0.5 meter, and we have to obtain this delta x. So we know shear stress equals to capital G, that is modulus of elasticity, times shearing strain here. Now we can write this thing from here, and this is, let me write it, 1.80 into 10 to the power 6 units equals to G, which will be 5.6 into 10 to the power 9 units. Let me check it once again. 5.6, okay, into 10 to the power 9. And then we have delta X times divided by L, which is 0.5. So the only thing we need to calculate it, and then we will have delta X in terms of meter. And if you go for it, it will be 1.6 into 10 to the power minus 4 meter. So this is all for this video.